In this short video presentation, we shall be focusing on ammonia derived from the Haber process and its use to make artificial fertilizers. Let's study the MEDSEC assessment criteria that we shall be covering in this short video presentation. In this video presentation, we shall be mainly focusing on MEDSEC assessment criteria 12.2f. I have still included all of the MEDSEC criteria that are covered by lesson 4 in its totality. Okay, this is lesson 4b, and in lesson 4b we shall be focusing via two videos: my own introductory video on the next slide and the main video on the final slide. Now, in the main video, the narrator discusses how ammonia is used in order to feed the world. He first explains about how high the world's population is. It's at 7 billion, and without that artificial fertilizer use, it would not be possible to sustain the world's population at such a high level. So that's the video that you shall be watching, the principal video on the final slide. But in the next slide, there is my own introductory video where I explain the gist, the main content of the video that you shall be seeing. Let's go on to my explanatory video next. So in the video on the next slide, you will be seeing a presentation about one of the important uses of ammonia from the Haber process. Ammonia is used to make fertilizers. About 80% of the ammonia produced by the Haber process is involved in fertilizer production. The reason why it is so important is that plants require nitrogen as soluble nitrates in the soil. Now, nitrogen as it is found in the atmosphere is useless. Nitrogen is N2. There is a triple bond, a triple covalent bond between the two nitrogen atoms, making that nitrogen in air inaccessible for plant use. Plants can only use soluble nitrate in the soil in order to make their proteins. Now, as you would have seen from the previous slides, the production of ammonia via the Haber process is an equilibrium, meaning that as soon as the ammonia starts to form, it then starts to break down and return back to its initial reactants. So nitrogen and hydrogen reacting together form ammonia. As soon as the ammonia builds up, it breaks down and reforms nitrogen and hydrogen to some extent. Now, industrial chemists don't like this, and they have used the science that we have obtained, okay, the knowledge, the scientific knowledge that we obtained from Le Chatelier, who is a chemist who found out that you can manipulate the equilibrium conditions, okay, of any equilibrium in order to either maximize the product or the reactants. So the video also goes into how chemists, industrial chemists, play around with the conditions, okay, mainly pressure and temperature, in order to optimize the yield of the process. Because after all, it is in the interest of the people who are running the ammonia production plant to maximize the yield of ammonia in order to stay in business and make the process profitable. Remember what we have stated in previous slides, that in order to shift the equilibrium over to the right, since you start off with 4 moles of gases, N2 and 3H2, 4 moles. In order to go to the right, where you have 2 moles of gases, a high pressure is required. Since you have a high pressure, the system tries to remove the high pressure, and it goes from 4 moles to 2 moles. Remember what we said about using a compromise temperature? The Haber process moving forward is exothermic, minus 92 kilojoules per mole are generated. So technically speaking, you should use a low temperature, because if you use a low temperature, the system likes to create more temperature, more heat, and it would do so by shifting to the right. But the problem of using too low a temperature would then be of slowing down the rate of reaction. So chemists use a compromised temperature. They use a temperature that is neither too high nor too low. It's around 450 Celsius. It is high enough to sustain the reaction rate at a fast enough rate, but not that high to shift the equilibrium back to the left, to the reactants. It still allows the reaction to move forward. Okay, I suggest that you now go on to viewing the video on the next slide, and if you need to return to this slide and video for any further clarification. Thank you.
What would you say is the most important discovery made in the past few centuries? Is it the computer, the car, electricity, or maybe the discovery of the atom? I would argue that it is this chemical reaction. A nitrogen gas molecule plus 3 hydrogen gas molecules gets you 2 ammonia gas molecules. This is the Haber process of binding nitrogen molecules in the air to hydrogen molecules, or turning air into fertilizer. Without this reaction, farmers would be capable of producing enough food for only 4 billion people. Our current population is just over 7 billion people. So without the Haber process, over 3 billion people would be without food. You see, nitrogen, in the form of nitrate, NO3, is an essential nutrient for plants to survive. As crops grow, they consume the nitrogen, removing it from the soil. The nitrogen can be replenished through long natural fertilization processes, like decaying animals, but humans want to grow food much faster than that. Now, here's the frustrating part. 78% of the air is composed of nitrogen, but crops can't just take nitrogen from the air because it contains very strong triple bonds, which crops cannot break. What Haber did, basically, was figure out a way to take this nitrogen in the air and put it into the ground. In 1908, the German chemist Fritz Haber developed a chemical method for utilizing the vast supply of nitrogen in the air. Haber found a method which took the nitrogen in the air and bonded it to hydrogen to form ammonia. Ammonia can then be injected into the soil, where it is quickly converted into nitrate. But if Haber's process was going to be used to feed the world, he would need to find a way to create a lot of this ammonia quickly and easily. In order to understand how Haber accomplished this feat, we need to know something about chemical equilibrium. Chemical equilibrium can be achieved when you have a reaction in a closed container. For example, let's say you put hydrogen and nitrogen into a closed container and allow them to react. In the beginning of the experiment, we have a lot of nitrogen and hydrogen, so the formation of ammonia proceeds at a high speed. But as the hydrogen and nitrogen react and get used up, the reaction slows down because there is less nitrogen and hydrogen in the container. Eventually, the ammonia molecules reach a point where they start to decompose back into the nitrogen and hydrogen. After a while, the two reactions, creating and breaking down ammonia, will reach the same speed. When these speeds are equal, we say the reaction has reached equilibrium. This might sound good, but it's not when what you want is to just create a ton of ammonia. Haber doesn't want the ammonia to break down at all, but if you simply leave the reaction in a closed container, that's what will happen. Here's where Henri Le Chatelier, a French chemist, can help. What he found was that if you take a system in equilibrium and you add something to it, like say nitrogen, the system will work to get back to equilibrium again. Le Chatelier also found that if you increase the amount of pressure on a system, the system tries to work to return to the pressure it had. It's like being in a crowded room. The more molecules there are, the more pressure there is. If we look back at our equation, we see that on the left-hand side, there are 4 molecules on the left and just 2 on the right. So if we want the room to be less crowded and therefore have less pressure, the system will start combining nitrogen and hydrogen to make the more compact ammonia molecules. Haber realized that in order to make large amounts of ammonia, he would have to create a machine that would continually add nitrogen and hydrogen, while also increasing the pressure on the equilibrium system, which is exactly what he did. Today, ammonia is one of the most produced chemical compounds in the world. Roughly 131 million metric tons are produced a year, which is about 290 billion pounds of ammonia. That's about the mass of 30 million African elephants, weighing roughly 10,000 pounds each. 80% of this ammonia is used in fertilizer production, while the rest is used in industrial and household cleaners, and to produce other nitrogen compounds, such as nitric acid. Recent studies have found that half of the nitrogen from these fertilizers is not assimilated by plants. Consequently, the nitrogen is found as a volatile chemical compound in the Earth's water supplies and atmosphere, severely damaging our environment. Of course, Haber did not foresee this problem when he introduced his invention. Following his pioneering vision, scientists today are looking for a new Haber process of the 21st century, which will reach the same level of aid without the dangerous consequences.